What specific problem does the proposed method address regarding the training of VQ-VAEs, and how does it improve on the issues associated with the straight-through estimator, STE?
The proposed method addresses the non-differentiability issue in training vector quantized variational autoencoders, VQ-VAEs, caused by the vector quantization layer, which hinders gradient flow during backpropagation. The straight-through estimator, SAINT, approximates gradients by copying them from the decoder's input to the encoder's output, but this leads to poor model performance and codebook collapse, where many codebook vectors become unused. In contrast, the proposed rotation trick allows for a smooth transformation of the encoder output to the nearest codebook vector, enabling gradients to flow back to the encoder without losing information about the encoder's output location relative to the codebook vector. This method preserves the angle between the gradient and the codebook vector, allowing for more nuanced updates that can either increase codebook usage or reduce quantization error, thus improving reconstruction performance and overall model effectiveness. Empirical results show that using the rotation trick significantly enhances reconstruction metrics and codebook utilization compared to the STE.
Can you explain the step-by-step mechanism of the rotation trick as described in the paper? What are the transformations involved, and how do they affect the gradient propagation during backpropagation?
The rotation trick involves a step-by-step mechanism to facilitate gradient propagation through the vector quantization layer in VQ-VAEs. First, for a given encoder output, E, and its nearest codebook vector, Q, the trick applies a rotation transformation, R, that aligns E with Q and rescales E to match the magnitude of Q. This is achieved by treating the rotation and rescaling as constants during differentiation, thus avoiding the need to compute gradients through these transformations. During backpropagation, instead of using the straight-through estimator, SAINT, which sets frac partial Q partial E to the identity matrix, the rotation trick sets frac partial Q partial E to a rotation and rescaling transformation that preserves the angle between the gradient, nabla_QL, and Q as it moves to E. This approach allows gradients to flow back to the encoder in a way that reflects the relative positions of E and Q, enabling more nuanced updates that can either push points within the same Voronoi region apart or pull them closer together, ultimately improving codebook utilization and reducing quantization error.
Provide a simple but illustrative example of how the rotation trick functions in practice, detailing how the gradients are adjusted during the backward pass for a given encoder output.
The rotation trick functions by transforming the encoder output, E, to the nearest codebook vector, Q, through a rotation and rescaling linear transformation. During the backward pass, instead of using the straight-through estimator, SAINT, which sets the gradient, frac partial Q partial E, to the identity matrix, the rotation trick adjusts this gradient based on the position of E relative to Q. Specifically, it preserves the angle between the gradient, nabla_QL, at Q, and the codebook vector, Q, as it moves to E. This means that if E is far from Q, the rotation trick can either pull E closer to Q or push it towards another codebook vector, depending on the direction of the gradient. This nuanced adjustment allows for better utilization of the codebook and reduces quantization error, as it effectively captures the relative positions of points within the same Voronoi region during gradient updates.
What are the empirical results obtained when applying the rotation trick in comparison to traditional methods like the STE and the Hessian approximation? Please include specific metrics and improvements noted in the experiments.
The empirical results from applying the rotation trick demonstrate significant improvements over traditional methods like the straight-through estimator, SAINT, and the Hessian approximation. Specifically, when training a VQ-VAE on ImageNet, the rotation trick reduced quantization error by over an order of magnitude, increased codebook usage from 2% to 9%, and improved reconstruction metrics, with the reconstruction fit improving from 5.0 to 1.6, and reconstruction is from 141.5 to 193. In the context of VQ-GANs, similar enhancements were observed, with substantial decreases in quantization error and improved codebook usage across both autoregressive and latent diffusion modeling paradigms. The Hessian approximation and exact gradient methods, while theoretically more accurate, resulted in poor reconstruction performance due to overfitting and a mismatch in training objectives, further underscoring the effectiveness of the rotation trick. Overall, the rotation trick not only enhances reconstruction quality, but also stabilizes training, preventing issues like codebook collapse that were prevalent with the STE.
What limitations did the authors encounter with the rotation trick, if any, and how do these limitations impact the practical implementations of VQ-VAEs?
The authors did not explicitly mention significant limitations of the rotation trick in the provided text. However, they did highlight that while the rotation trick improves reconstruction performance and codebook utilization, it does not change the output of the forward pass. This means that any improvements in training dynamics and gradient propagation do not alter the fundamental architecture or the expected outputs of the VQ-VAE. Additionally, the authors noted that using alternative methods like the Hessian approximation or exact gradients resulted in poor performance due to overfitting and a mismatch in training objectives between the encoder and decoder. This suggests that while the rotation trick is beneficial, practical implementations of VQ-VAEs must still be cautious about maintaining a balance between gradient accuracy and model generalization to avoid potential pitfalls in training stability and performance.
In the context of future work, what potential developments or refinements do the authors suggest to further enhance the performance of VQ-VAEs using the rotation trick approach?
The authors suggest several potential developments to enhance the performance of VQ-VAEs using the rotation trick approach. They indicate that further exploration of the rotation trick's effects on different configurations of VQ-VAEs could yield additional insights, particularly in how it influences codebook utilization and quantization error across various datasets and tasks. Additionally, they mention the possibility of integrating the rotation trick with other methods that improve codebook model interactions, such as those that employ different distance metrics or dynamic codebook selection. The authors also highlight the need for a deeper analysis of the rotation trick's impact on the training stability and generalization of VQ-VAEs, especially in complex models like VQ-GANs and VT-VQ-GANs. Lastly, they imply that future work could investigate the theoretical underpinnings of the rotation trick to better understand its advantages over traditional methods like the straight-through estimator, STE.